Hello friends, welcome you all to the 55th lecture on functional analysis and its applications. In this lecture, we will discuss the uniform boundedness principle. These are the contents of today's lecture. Basic definitions and uniform boundedness principle. That is uniform boundedness principle on bounded linear transformation. These are the basic definitions which will be used in further lectures. Definition first, open sphere. Let Xd be the given metric space. Let x0 belonging to x and R be any positive real number. Then the open sphere with the center x0 and radius r is a subset of x defined by yes x0 r yes r x0 equal to x is the element of x such that dxx0 less than r. Closed sphere. Let Xd be the given metric space and x0 belonging to x and r be any non-negative real number. Then the closed sphere with center at x0 and radius r is defined as S in closed bracket x0r. This is the notation for closed sphere. Okay. This is also denoted by SR x0 in closed bracket. It is defined as x is the element of x such that dxx0 less or equal to r. In open sphere, this is dxx0 less than r. In closed sphere, this is dxx0 less or equal to r. Okay. Open set. A subset G of a metric space XD is called an open set if given any point x belonging to G, then there exists a positive real number R such that yes xr, that is open sphere, is the proper subset of G, that is each point of G is the center of some open sphere contained in G. Next definition, neighborhood. Let Xd be a metric space and let x belonging to x. A subset n of x is said to be neighborhood of x if there exists an open set G such that x belonging to G is proper subset of n. Next definition, limit point. A point x in Xd is called a limit point of a subset A of x if every neighborhood of x contains a point of A distinct from x. Closed set. A subset F of metric space X is called a closed set if it contains all its limit points. Noting point. A subset F of metric space X is called a closed set if the complement of F is open set. Second point. Any closed sphere in metric space is closed set. Closure. Let A be a subset of metric space X. The closure of A, denoted by A bar, is the intersection of all closed sets containing A. That is, A bar equal to intersection of F such that F is closed and F is superset of A. It follows that A bar is the smallest closed set containing A. Interior point. Let A be a subset of Xd. A point x0 belonging to A is called an interior point of A if it is the center of some open sphere contained in A. The set of all interior points of A is called the interior of A, denoted by int A or A circle. Homeomorphism. A homeomorphism is a function f such that x to y, that is continuous one-to-one and has a continuous inverse function, that is f inverse such that y to x. Noting point. For a bijection f such that x to y is a homeomorphism if f of the closure of h equal to closure of the f of h, that is f of h bar is equal to bar of fh. Bar notation for the closure. For all h is a subset of h. Here h bar denotes the closure of h. Bare category theorem. If a complete metric space is the union of a sequence of its subsets, then the closure of at least one set in the sequence must have a non-empty interior. The uniform boundedness principle. It is also known as Banach-Steinhaus theorem. Let B be a Banach space and N be a normed linear space. If Ti is a non-empty set of a continuous linear transformations of B into N with the property that Tix is a bounded subset of N for each vector x belonging to P, then norm Ti is a bounded set, that is Ti is bounded as subset of beta Bn. Proof. We prove the theorem in the following three steps. For each positive integer n, define Fn equal to x such that x belonging to B, Banach space B, and norm Tix less or equal to n for all I. Equation 1. Step 1. We prove that Fn is closed subset of B for each fixed n as let x belonging to Fn if and only if norm Tix less or equal to n. Okay. Here x is the element of Fn, then norm Tix less or equal to n. Norm Tix less or equal to n. It means Tix is the element of closed sphere with center 0 with radius n. Okay. Sn0 is the closed sphere in n with center 0, that is origin, and radius n. Okay. That is, by this we can write x is the element of Ti inverse Sn0. Okay. If and only if x is the element of intersection I Ti inverse Sn0, because equation 1 is true for all I. Okay. So meaning of this here, x belonging to Fn and x belonging to intersection of Ti inverse Sn0. Okay. It means Fn is a subset of the intersection of Ti inverse Sn0. This condition if and only if, it means reverse also true if x belonging to Ti inverse Sn0 and then x belonging to Fn. It means Ti inverse Sn0 is subset of Fn. So that Fn is equal to intersection of Ti inverse Sn0, which is closed being an intersection of closed sets. Note that since each Ti is continuous and Sn0 is closed in N, each T inverse Sn0 is closed in P. Okay, so this is Ti inverse. Step 2. In this step, we show that B is equal to union of Fn, where n is equal to 1 to infinity. We prove it by contradiction. For if B not equal to union of Fn, then there exists some x belonging to B such that x is not an element of Fn. Okay, here x belonging to Fn, then norm Tix less or equal to n. Here in our assumption, x not belonging to Fn, then norm Tix greater than n for all I. This implies that the set Tix is not bounded, which contradicts the hypothesis. Hence, we must have B is equal to union of Fn, so that the complete space B is the union of the sequence of its subsets Fn. Step 3. We complete the proof by bare category theorem. What is bare category theorem? Already it has been defined in definitions. Okay, a complete metric space is the union of a sequence of its subsets, then the closure of at least one set in the sequence must have a non-empty interior. This is the bare category theorem. By bare category theorem, there exists an integer n0 such that closure of f n0 had non-empty interior. Okay, because here closure at least one set in the sequence must have non-empty interior. Since Fn0 is closed, we have closure of Fn0 is equal to Fn0, and so Fn0 must have non-empty interior. That is, there exists some x0 belonging to Fn0, so that Fn0 is a neighborhood of x0. Since Fn0 is closed, there exists a closed sphere S or x0 with center x0 and radius r0, which is defined as S r0 x0 is equal to x, such that x belonging to B. Norm x minus x0 less or equal to r0 is subset of Fn0. Okay, this is equation 2. Let x belonging to B be arbitrary and x not equal to 0. Let us take z equal to x0 plus rx, where r is defined r0 upon 2 norm x. Okay, that is a positive real number. Then norm of z minus x0 equal to norm of rx. Here r is positive real number, so this can be written as r into norm x. Okay, here r equal to r0 upon 2 norm x. So r0 upon 2 norm x into norm x, that is r0 by 2. Okay, so norm z minus x0 equal to R0 by 2. This shows that Z is the element of closed sphere SRX0. Okay. Now from equation 2 and from the definition of Fn0, we have norm Tij less or equal to N0. Okay. We have the definition of Fn is this one, Tix less or equal to N. And here for Fn0, Z belonging to closed sphere SR0X0, then norm of Tij less or equal to N0. Okay. Since X0 also belonging to SR0X0, so we have norm Tix0 less or equal to N0. Now from equation 3, we get x is equal to z minus x0 upon r for any x belonging to B. Hence for any x belonging to B and x not equal to 0, we get for all I norm Tix equal to norm of Ti z minus x0 upon r. Okay, because here x is equal to this z minus x0 upon r. Okay, so r is a positive real number, Ti is linear, so we can write 1 upon r Tiz minus x0. And also we know that norm alpha x is equal to mod alpha norm x. So here alpha is positive real number. So we can write this is without of mod. That is, this can be written as 1 upon r norm of Ti of z minus x0. Okay. So this can be written as 1 upon r norm of Ti z minus Ti x 0. Okay. So this is type of norm of x plus y, and we know that norm of x plus y less or equal to norm x plus norm y. Okay. So as per this one can be written as norm of Tiz plus norm of Ti x0. Okay. Using equation 4, norm Tiz less or equal to N0, and by equation 5 norm Tix0 also less or equal to N0. So we get norm of Tix less or equal to 1 upon r into N0 plus N0. Okay. So this 2 N0 by r. Again putting the value of r from equation 3. R equal to R0 upon 2 norm x. Okay. So we have 4 N0 upon R0 into norm x. So norm Tix less or equal to 4 N0 upon R0 into norm x. So this is the type of norm of Tix less or equal to K norm x, where K is positive constant. Okay. So this shows that Tix is the bounded linear transformation. Okay. Hence for all I, we divide it by norm x, we get norm tx by norm x less or equal to k. So, supremum of norm tix upon norm x less or equal to k. Supremum of norm tix upon norm x, it is denoted by norm ti. Therefore, norm ti is equal to supremum of norm tix upon norm x less or equal to k. It follows that norm ti is a bounded set of numbers, or ti is bounded as a subset of beta Bn. Here in statement, we have to prove that norm tix is a bounded subset of n for each x belonging to B, then norm T is bounded set. So here we have proved norm tix less or equal to k norm x, that is Ti is bounded linear transformation with the property that norm Ti equal to supremum of norm tix upon norm x less or equal to k. This shows that the norm Ti is bounded set of numbers. This completes the proof of the theorem. In this lecture, we have discussed the basic definitions and uniform boundedness principle. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narsey. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterroot. Thank you.